Students, let us continue with the problems on design of tension member. A tension member consists of two angles, ISA 90 by 90 by 8 mm bolted to 10 mm gusset plate, one on each side using single rows of bolt and tacked bolt. Determine the maximum load that the member can carry. What will be the load carrying if the angles are connected on the same side of the gusset plate? So two cases we have. First, let us take the first case. Angles are connected on both sides of the gusset plate. So when the angles are connected on both sides of the gusset plate, this is how the figure looks like. The size of the angle is it is an equal angle 90 by 90 by 8 mm. This is a single row of bolt placed here. 10 mm is the thickness of the gusset plate. Now diameter of the bolt is not given. Let us calculate diameter of the bolt using a formula 6 into root of t. T is the thickness of the plate or thickness of the angle. So this is equal to 10.9, so 18.9 mm. So let us provide the diameter of the bolt as 20 mm. Therefore, diameter of the bolt becomes 22 mm. Now, tension capacity of the member is the minimum of these three: gross yielding, net rupture, and block shear capacity. First, let us calculate gross yielding of the section from class 6.3.1, page number 40. We have TDG equal to AGFY divided by gamma m naught. AG is the gross area. Gross area for two angles separately we have to consider. So 2 into 1379. This 1379 can be taken from the steel table, or you can also calculate 2 into 90 minus 8 by 2 plus 8 plus 90 minus 8 by 2 into 8 into 2, that is 2758 millimeter square. Therefore, TGD equal to 626.818 kilonewton. Now you calculate the net rupture of the section TDN from 6.3.3, page number 33. So using double angles, whenever we have the double angles, TDN equal to alpha into AN into FU divided by gamma M1. So alpha value from the code book, if it is 1 bolt 0.6, 2 bolts 0.6, again 3 bolts it is 0.7. If it is 4 and more bolt it is zero point 0.8, and for welded connection in the previous problem we have seen alpha equal to 0.8. Now let us assume the required number of bolts is more than 4 and the capacity is more than 600 km. Therefore, alpha is taken as zero point 0.8. Now, AN is the net area of the section. The net area, whenever you have this bolted connection, you have to reduce the bolt diameter here. So, AN equal to 2 into net area of the connected leg plus net area of the outstanding leg of the angle. So an equal to 2 into 90 minus 8 by 2 minus 22 into 8. 8 is the thickness, plus 90 minus 8 by 2 into 8. Here no need to minus 22 or no need to deduct 22, because I have the bolt holes only present on the connected leg. So the first part is for connected leg, second part is for the outstanding leg. So the area is 2400 millimeters square. Calculate TDN. 0.8 into 2400 into 410 divided by 1.25. It is 629 kilonewtons. The unit is wrong. It should be kilonewtons. Now, the block shear strength TDB I have to calculate for bolted connections. The formula is TDB1 equal to AVGFY divided by root 3 gamma m naught plus 0.9 AVN into FU divided by gamma m1. TDB2 equal to 0.9 AVN FU divided by root 3 gamma m1 plus ATG Fy divided by gamma m1. So here, before going for the calculation of tension strength because of the block shear, I have to calculate total number of bolts required. So to calculate the number of bolts required, I can I mean to calculate the number of bolts, the applied tension load or the tension capacity of the plate divided by the bolt value I have to do. This is the load, tensile load, divided by bolt value is the number of bolt. So TD is the minimum of TDG and TDN. So minimum is 626.818. So one value is known. Now I have to calculate the bolt value. So bolt value you know how to calculate. These are already discussed in the module 1 bolted connection. So first you calculate the shear capacity VDSB. The VTSB is nothing but VNSB by gamma NB. So assuming ASB is 0, so you calculate these values. Okay, ASB is considered as 0 because NS is taken as 0. So VDSB works out to be 90.544 kilonewton, and the bearing capacity of the bolt or capacity of the bolt in bearing works out to be 2.5 kb dt fu divided by gamma mb. So for calculation purpose we will take kb equal to 0.5. Otherwise you need to calculate the edge distance and pitch distance, then you have to calculate the kb value. Kb value is the least of four values, so you know. So if we get vdpb equal to 82 kilonewton, out of vdpb and vdsb, the minimum value is the bolt value, so the bolt value is 82 kilonewton. Therefore number of bolt equal to 626, that is a td divided by bolt value, it is approximately 8 numbers. 7 point you will get, we will take it as 8 numbers. So in this particular angle section, I have to accommodate totally 8 number of bolts. So 2 2 2 2, totally it is 8. Now the edge distance is taken as 1.5 times d naught, that is 35 mm we get, and pitch distance is taken as 2.5 times the diameter of the bolt, it is 50 mm. So let me go with these values. So the gauge distance will be 90 by 2 plus 4, it is plus 8, it is 55 mm. Okay. Now, as per figure number 7b, page number 34, the failure path of the angle for block shear will be like this. This is how the failure path for the block shear. So here you calculate LC. LC is nothing but 385. How we got 385? You have to calculate the distance from here to here. 385 minus 7.5 into d naught. So totally I have a 7 full bolt diameter coming here and half of this 8th bolt coming. So it is 7.5 d naught. How I got 385? 385 is nothing but 50 plus 50 plus 50 plus 50. So totally 350 plus 35. It is 385. So 385 minus 7.5 into 22, it is 220 mm, that is LC. LV is 35 plus 7 into 50, so it is 385. Okay, then Ln is distance from here to here, Lt is distance from here to here, it is 35 mm. Ln is 35 minus half of the diameter of the hole, it is 24 mm. So AVG is nothing but LV into T. AVG is nothing but LV into T, gross area it is. So it is 3080 millimeter square. AVN is 1760 millimeter square. LC into T. ATN is LN into T. And ATG is LT into T. You calculate these values. Now TDB1 will be equal to 460.8 kilonewton and TDB2 is equal to 363.59. So here actually two angles are connected, therefore these values shall be multiplied with the 2. Therefore TDB is the minimum of these two, works out to be 727.198. Therefore tension capacity is the least of the above three values. One is gross yielding, then the rupture of the neck section, and the third one is the block shear failure. So 626.818 is the TD value. Now imagine if the angles are connected on the same side of the gusset plate, then the strength, gross strength will remain as it is 626.818 as the previous one. The net rupture also will remain the same as the previous one. However, the angles are connected on the same side of the gusset plate, then there will be only one shear plane in the joint. Then there will be only one shear plane in the joint. Therefore, the bolt value is the minimum of shear capacity. So that is nothing but 90.5 to divided by 2 it will be. Okay. When you have one shear plane, automatically you will get the 2. It is to be divided with the 2. So 45.27. Now the bearing capacity is given by 82.82 kilonewton and bolt value is 45.27 kilonewton. Therefore, number of bolts required equal to 626.8 divided by 45.27, that is the bolt value. So approximately we get 14 numbers of bolt. So by referring to the figure 7b of page number 34, you calculate these values LV, LC, then LN and LT. So after calculating, you calculate TDB1 and TDB2. Okay. Then you get the axial tensile force or tension capacity as same 626.818 kilonewton itself. Now, if the tack bolt is provided and the angles are connected on the uh, same side of the gusset plate, then what will happen? The diameter of the bolt is 20 mm and diameter of the hole is 22. So TDG will remain 626 only. The block shear only is the calculation is different. Now the block shear TDN equal to alpha n AN into FU divided by gamma m1. So here alpha is taken as 0.8. So upon substitution, the AN value you have to calculate Then we get TDN equal to 537.395 kilonewton.